In this tutorial we will discuss DC polarography. Let's start with basic principle of DC polarography. Polarography is the most extensively studied and used voltammetric method in which working electrode takes the form of a series of tiny drops of mercury issuing from a fine glass capillary called the dropping mercury electrode DME. In this polarography, potential is applied in the form of voltage. And due to applied voltage, the analyte present in the solution will diffuse, due to which diffusion current will produce. Dropping mercury act as cathode, which is negatively charged and polarizable. And mercury pools act as anode, which is positively charged and non-polarizable. Air such as nitrogen is used to eliminate the oxygen present in sample. Instrumentation of DC polarography. It consists of dropping mercury electrode with diameter of capillary of range 20 to 50 micrometers and droplet time is 2 to 12 seconds, so 5 to 30 drops per minute can be produced. The applied potential range is plus 0.4 to minus 1.8 volt. And supporting electrolytes are used to minimize the migration current. And the supporting electrolyte concentration will be 50 to 100 times greater than analyte. The mercury pool has high surface area, no change in potential and non-polarizable electrode. If drop size is small, the number of drops will increase, which can't be measured, and larger drop lead to more convection, which changes the thickness and current. Current produced in DC polarography. Diffusion current. This current is acquired by the diffusion of the ions from the sample solution to the surface of the electrode. This current is produced generally due to the concentration gradient. And this is generally denoted by ID. Residual current. The current that flows in the absence of the sample material is known as the residual current. This current is produced due to the presence of impurities. And this is generally denoted by IR. Migration current. This current is produced due to the migration of the oxidizable or reducible ions, which is proportional to the potential gradient. This is because of the proportion of the analyte. This can be removed by the addition of the supporting electrolyte solution. And this is generally denoted by IM. Limiting current. This is total of the diffusion current and the migration current. This is caused by the depletion of the oxidizable or reducible ions at the electrode surface. In this, the current is steady where the diffusion of ions is equal to the rate of reduction. This is reached by the complete saturation of the electrode. And this is generally denoted by IL. Advantages of using DME. Its surface is reproducible, smooth, and continuously renewed. And it eliminates or minimizes the contamination possibility. Most metals can be reduced at mercury drop to form amalgam. The potential at which water is reduced is very negative. This further broadens the number of metal ions which can be analyzed by polarography. The surface area can be easily known from the weight of the drops. The large hydrogen overvoltage on mercury renders possible deposition of alkali metal ions such as aluminum ion Al+3, manganese ion Mn+2, etc. And it is liquid at room temperature. The actual potential window is extending. And this is very suitable for field, etc. Disadvantages of using DME. It is highly toxic. The size of drop changes with time and complicates the electrochemistry. In the presence of ions, it forms PPT or complexes with mercury even at low potential. The DME is difficult to use and tends to malfunction as a result of clogging. And finally, due to oxidation of mercury, the electrode cannot be used at more positive potentials, etc.